Let's try that. All right, are there any questions on homework? Nathan,
We go over like 15.
number 15, can you show it?
Yeah, it's
This is awesome. To see the problems there I posted.
yeah, it's the x minus 2 to the n.
Over n squared plus 1.
Yeah.
X minus 2 to the n over n squared plus 1. So this is in the form of the second kind of power series we talked about in x minus a, centered at 2. And so we're going to use the ratio test. Because the power is just n, and the absolute value of x minus 2 will come out. Do I need to explain that? Or are you comfortable with that? Okay? And then we have the limit as n goes to infinity. The n plus first term divided by, or we always invert and multiply, nth term. Okay? Something like that. So, two shortcuts that I've been encouraging us to take. One is to recognize what's going to happen with the power, with the variable part, the x minus 2 in this case, and that is one of them is going to survive. And the other thing is to invert and multiply and save a step. Now, as n goes to infinity, this is a second degree polynomial divided by a second degree polynomial. What's the limit?
It's 1.
It's 1. It's the ratio of the leading coefficients, 1 and 1. So all of this stuff is just 1. Therefore, you get just the absolute value of x minus 2. And this is the ratio test, so we need it for convergence, we need it to be less than 1. So it converges if x minus 2 is between -1 and 1. Perfect. Okay, Nathan? Are you with me so far? Everything good?
Then we add 2 to both sides.
Add 2, and so we get 1 less than x less than 3. So the radius is 1. The interval is 1 to 3, and we need to examine the endpoints. Right? We could tack on the endpoints. So if x equals 3, I get the summation. 3 minus 2 is 1. The power n over n squared plus 1. This 1 over n squared. Does that converge or diverge?
It converges because it behaves like the P series where we have the sum of the reciprocals of squares.
Yeah, it's a P series almost. If we cover the 1 up, and the 1 becomes insignificant. So this converges less than infinity, and we could do a literal comparison. The terms here are smaller than 1 over n squared because we're making the denominator bigger. Or the easy way to do it is limit comparison. So that this converges, and we could use either comparison test. The other endpoint, x equals 1. Now we get the summation. Plug in 1, we get -1 to the n.
And then we can use the alternating series test.
Yeah, that converges also. Alternating series test. Terms go to 0. They decrease. No mystery. I mean, we just showed it converged in absolute value, therefore it converges. We know that. And so here's our answer. The radius is 1. The interval, we're going to include both endpoints, 1 to 3, and every number in between. Okay, Nathan? Matthew? It? What do you mean by it?
The limit.
Yes,
How is that? Is that taken away?
all right, so the value of the limit is the absolute value of x minus 10. Okay? And then we just solve that in, we need that to be less than 1 for the ratio test. Okay, any other questions? All right. Let's find an eraser. Although, I don't need it. So today we'll say some things, we'll finish section 1 and then add a little bit in section 2. We'll just make it all run together. All right, so we have a power series. A and x to the. It could be in, centered at 0 like this one, or centered at some other number like the one they asked about. We know how to deal with that. So it doesn't create any confusion for us whatsoever. This power series converges. It has an interval. It converges. It's finite on an interval like minus r to r. And for discussion, let's assume that r is a positive number. The ones where r is 0 are not very interesting series. And it could be infinity, and that's okay with us as well. It's not 0. All right, so for every x in that interval, that series adds up to a number, a finite value. So it's easy for us to think about this. Well, it's just some function. To find the functional value, all I need to do is plug that x value in and find out what the series converges to. And what we want to do now is investigate. For what power series can we literally find that function for? Okay? Remember, when we first started out, we were able to find the sums of series that converge. Geometric, super powerful technique. Probably worth at least 20 points on the next exam if you just can manipulate geometric series. And then for some isolated others, we can find the sum. And then remember, I said we're going to forget about finding the sum for a while. We're just going to focus on, do they converge or do they diverge? And that's where we've been. And maybe it's not such a satisfying place to have the problems conclude with the facts, oh, it converges or it diverges. Like, what does it converge to? Very much more interesting. And I told you someday we're going to be more interested in what it converges to. And today is that day. All right, so what we want to do is find connections between a power series when it converges and the function. Does this concept make sense to you, that we can think of, because there are x involved here, we can think of this as a function? And it makes sense as long as this series converges, then the function has a value. If the series doesn't converge, there's no functional value there. There's no value. All right, so that's what we're going to investigate. And we're going to start with a super easy one. And then we're going to learn some things we can do to that to expand the kind of power series for which we can find a function. And this equal sign, they're the same thing. If I can find the function, then I can find the value the series converges to for every value in the interval. All right, so we're going to start with an easy one. Say easy because it's geometric. And we're experts. Geometric. All right. I'll write it out long form, and then we'll write it in sigma. 1 plus x squared. So I'm going to pick every coefficient to be 1. That is a geometric series. It converges to the first term. 1 minus r. Whatever 1 minus x, that's my function. I said I would write it in sigma form. X to the n equals 0 to infinity. Here's our power series, and here's the function it converges to. Okay, not for all x. It's geometric, so we need x to be in the interval -1. When x equals 2, what I just wrote down is completely meaningless. But when x equals 1/2, I wrote a true statement. You can pick any number between -1 and 1, and this series converges to that number. Okay? Now, all I've done is restate something we already knew. But like I said before, what we want to do now is to kind of play around with it a little bit and see if we can come up with some more series and the functions they converge to. So we're going to learn some manipulations that we can do. The first one, some manipulations, it's probably a better word than that, that preserve convergence. So if we start with convergence, and we're going to start right there, and I do the manipulation, I still get convergence. Okay? There are, I think, 3 sort of, maybe 4 that we'll talk about. The first one is composition. With a new function, a linear function, some number a times x. Okay? So it preserves convergence as long as the thing I'm composing f with, as long as ax, let me say this. The thing that I plug into that function, it has to be between -1 and 1. So that's going to have to be true for us. And I'll do several examples. Okay. In fact, we'll do the examples before I list out the other manipulations. So, example, find y these. Let's say this one. Find power series that converge to these and identify the interval of convergence. So here's the first one. 1/1 plus x. So let me say for the video I'm recording, some of the examples we do are going to be important for the continued work. Some of them are just to give us a chance to practice. I'm going to make a list of the important ones on the sideboard. You won't be able to see it on the video, but students here in class today will help me remember to show the side panel when class is done so that you can freeze in time the important results. The first one is the one we just, we're going to start with 1 over 1 minus x, 1 plus x. Sigma form, x to the n equals 0 to infinity. And it's only true for x's between -1. Right. All right, so I look at this guy and say, how can I manipulate the one we know, the series 4, 1 over 1 minus x, by a composition like this? Will has an idea.
Substitute x for negative x.
Substitute x for negative x. That's right. This function is f of negative x using for f, what we came up with over here. So all I have to do is replace all the x's with negative x. No problem. That's going to look like, when the power is even, the minus sign goes away. And when the power is odd, it survives. So we're going to get 1 minus x plus x squared minus x cubed in sigma form. -1 to the n equals 0 to infinity x to the n. And because, we need the thing we're plugging in to be between -1 and 1, right? That's where this series converges. And then we solve that inequality by multiplying by -1 and you just get the same thing. All right, we're going to declare that's an important one. Another way of justifying that interval is saying, well, if x is between -1 and 1, so is minus x. So we could do it algebraically, or we could just do it by thinking a little bit about it. Okay, so for every x between -1 and 1, this series converges to that function. All right, part B. Are there any questions? All right, let's find one for 1 plus 3x.
You substitute just substitute x for 3x.
Maybe the other way around. Again, using our original starting point, f 1 over 1 minus x, that function that comes from the basic geometric series. I see that I can write this function as that function f composed with -3x. Or I could call this function g. And then I say, well, this is just g of 3x. Right? This has the built-in, the minus sign already built into it. Either way, we can go. And so, like Will said, let's use the g form. We're just going to replace x with 3x. Okay, so we get 1 minus 3x plus 3x squared minus 3x all cubed, so on. I don't know, we can, I guess, multiply it out. We can write it in sigma form. It alternates. Start positive, then we get 3 to the n, x to the n, I believe. Starting at 0 and going to infinity. But what do I have yet to figure out? The interval. Like if I triple all of my X values before I plug them in, it's probably going to affect the interval. Well, the thing I'm plugging in, 3X, it's got to be between -1 and 1 because I'm plugging it into a geometric series. If the thing I'm plugging in is bigger than 1 or less than -1, it diverges. So I need to find the X values. How do I go from here to the
Divide
X?
by 3.
Divide by 3, absolutely. -1/3. So I get that it converges to this function, 1/1 plus 3x. This series converges for every x between -1/3 and +1/3, and it converges to that function, 1/1 plus 3. Okay, so I can expand, can change the multiple of x at the price of changing the interval of actually the radius of convergence. So notice what we get down here is that the radius is only 1/3. In order to keep the ratio of the geometry between -1 and 1. Are there any questions? Matthew?
Still in the first, like, number 1.
Uh-huh.
I am receiving 1 plus x squared, so on is sum, is equal to the sum. But how is it equal to 1/1 minus x?
Because it's a geometric series. The ratio is x. Right? We're experts at geometric series. You better be by Wednesday. You'll regret it if you're not. Geometric series are easy. They converge if and only if r is between -1 and 1. And what do they converge to? The first term over 1 minus r. Like, we completely, 100%, totally, with no doubt, know how to analyze geometric series. So the only worrying thing, the only way to go wrong is we need to recognize them when we see one. Right? And then life is easy. So I just did erase it, but here's another one. That's a geometric series. R, what's R for this one?
X,
Not X,
and negative x.
negative X. I could have used that, but instead I wanted to illustrate how we can manipulate series and come up with a thing it converges to. This guy is not a geometric series. It is. I lied to you. The ratio there is -3x. We have to ensure that it's between -1. Okay? Does that answer your question? Yeah. Now we're going to learn these manipulations and we're going to apply them to series that we have already found out information about. That's why I'm compiling the list of important ones. So we can go back and say, oh, look, here's one of these we said is important. Here's what we can do with it. That's what part B was. We took this series, which we declared important by writing it over there. You'll be able to see it on the video at the end. And then we said, oh, look, let's do something else. And so we started with what we had previously figured out and declared was important. And then we did something to it. And we came up with a new thing. And by the way, I'm not going to declare this one's important. It's just an example of, what happens if this number is not 1 or -1. It changes the interval. Okay. Any other questions? The second manipulation. multiplied by some constant times x to a power. We use n a lot. Let me use like k. We use k a lot. We don't usually use n. So here's what I mean. We're going to take a function we know. Let's pick on the second one again. And then I'm going to multiply it by something like 3x squared, which gets me the new function, new in the sense that we don't know a power series for it. So I want to now find a power series for this guy. And the way we're going to do it is exactly how I constructed the function. I know a power series for this one. It made my important list over yonder. And then I'm just going to multiply it by 3x squared. And I can distribute that 3x squared inside if I want. So we're going to take 3x squared. We're going to multiply by the power series form. We look over on our list. Oh, yeah, there it is. 1 minus x plus x squared minus x cubed. We need x to be between -1 and 1 for it to be meaningful. And then we just distribute 3x squared. 3x squared minus 3x cubed plus 3x to the 4th minus 3x to the 5th, so on. And it's always good for us to write it in sigma form. Notice the powers start at 2. So let's start our index at 2. They alternate. The first term is positive. The first index value is even. So I can just say n. That's going to start positive and then turn negative, back and forth. And then I get a constant 3 times x to the n. And there we have it. A power series that converges to this function. As long as x is between -1 and 1. Yeah. There is no single correct way to write these sigmas. For example, I could say, well, I want my sum to start at 0. That's what I always do. And then I need to build the 2 up. So I'm just going to say n plus 2. And now everything is fine. So there's no like correct, accepted, perfect way to write sigmas. There are right ways to write it and there are wrong ways. Make sure you get a right way, a correct way. I don't have any particular care about which way you choose to write it as long as it's correct. All right, I want to do one more little tweak of the first one and then we'll try to get to the second and third one. I can do the same. So we're thinking of combining 1 and 2. Like we're still at this kind of algebraic manipulation. And we can also follow this process for something like x squared. For any power, actually. Oh, I'm going to illustrate for x squared because I have one more I want to write over here on the important category. I'll leave this because we're going to use it for, I think we're up to the next example. I don't know. Find power series for this function. One over 1 plus x squared. So we're going to take the f that we started with and compose it with g. So wherever the x shows up, I'm going to replace that x with x squared. But composing this function with that. Okay, so I'm going to get 1, no change there, but then I get an x squared. And then I get an x to the 4th, x squared squared. We're plugging in x squared for all the x's, minus x to the 6th. And that's going to be good as long as the thing that I'm plugging in is between -1 and 1, because I'm starting with a series that has that condition on it. But for what x's will x squared lie between -1 and 1?
Between 0 and 1.
Okay, you're going backwards. So we'll notice what x squared actually can't be negative. So why did I write that? Well, I'm plugging in x squared, and I know, whatever I plug in, it needs to be between -1 and 1. So because of the square, in actuality, the thing I'm plugging in, x squared, is going to be between 0 and 1. But, even if we think about that, so I'm thinking, okay, here I am. I need that to be true or equal. And what x is going to make that true? Pardon? How about if x equals -1/2? X squared is x squared. If x is -1/2 squared is that between 0 and 1? Yes, it is. So what do you think? If the x's that satisfy this are exactly these. If x is between -1 and 0, when you square it, you get 0. So the interval is the same, and we get our third important result. Equals 1 minus x squared plus x to the 4th minus sigma form. We can start at 0. It alternates, starts positive, and then we get x to the 2. And it converges only on -1. Oh, it's right. Any questions? So are you understanding the big picture? We're trying to find, actually you can look at it from either direction. We're trying to find the function that power series converges to, or given a function, we're trying to find the power series that converges to. We can start with either direction, either the function or the power series. We are starting so far with the function. We're trying to find a power series. Do you have a question?
So isn't that one the derivative of the?
It is amazing that you should say that. Manipulation number 3. I'm going to give you 3 and 4 at the same time because they're similar. If f of x equals summation a(n) x to the n. So I found a power series that converges to f on an interval. I'll just say on I, it's an interval. We know it's centered at 0, right? Because we learned on Wednesday that power series converge on these symmetric intervals, or all real numbers possibly. Then f prime of x equals summation a(n) times n x to the n minus 1 on 12. I can differentiate You see, inside the sigma, I took the derivative term by term. Whereas for the function, we have x to the n. For this derivative, we have n x to the n minus 1. I took the derivative. Okay, and we still get convergence. The only difference is if this guy does not converge at the endpoints, this one might, maybe, at the endpoints. 4. Start with the same premise. The f of x is summation a and x to the. Then we can integrate. Integral, this is an indefinite, equals the summation a, and we can do it term by term, n plus 1 over n plus 1. And it will still converge on the interior, guaranteed, of the interval, possibly at endpoints. We need to examine. So I can differentiate and integrate power series and preserve convergence on the interior of the interval of convergence. Possibly we'll get convergence at the endpoints. That's where we learn, we apply the things we learned in the previous chapter to determine does that series converge or not. If it does, it will certainly converge to the function that we just found. Now, maybe you're thinking, wait a minute, there's like an arbitrary constant when I find an antiderivative, and what are we going to do with that constant? Well, most of the time, I'll let you know if we run into an exception. We're going to choose 0 for the constant of integration. Okay, we'll start there, but we'll start by ignoring it. And if we run into one where we can't ignore it, I'll make a big deal out of it. And how about this? I'll promise you there won't be one before next Wednesday's exam. All right, I have 2 more examples. And then we'll be about out of time. Find a power series for the inverse tangent of x. Ln of 1 plus x. We'll start with the inverse tangent of x. So how do I go from the 3 important series on the left using the 4 manipulations we've learned to get to the inverse tangent? I should say, you probably don't need to use all 4 of them, maybe just one of them. And so since we know 1 over 1 plus x squared, we should use the antiderivative, the last one that I showed you. Yeah. So we know, because it's on the list of important ones, 1 over 1 plus x squared. I'm going to write it out in long form equal 1 minus x squared plus x to the 4th minus x to the 6th. Now integrate. I get the inverse tangent of x plus 0, the constant. On the right, I just do it term by term. X minus 1/3 x cubed plus 1/5 x to the 5th. And then it converges on minus 1 to 1. It actually converges at one of the endpoints. Which one?
Minus 1.
Minus 1. Yeah, we get an alternating series. The terms go to 0, 1/3, 1/5, 1/7. So what's included? Now, I'm sorry, it converges at the upper endpoint. Because it's already alternating. The lower endpoint cancels out the alternate, makes all the terms negative. And it will diverge there. It's like the harmonic. So 1 is on the interval here. I can plug it in and I get a true statement. If I plug in 1, I get 1 minus 1/3 plus 1/5 minus 1/7, which converges based on our work to the inverse tangent of 1. What is the inverse tangent of 1?
It's pi over 4.
Pi over 4. And just for the fun of it, let's multiply by 4. And what have we found?
Formula for pi.
Yeah. You hear about people who try to memorize the first 100 or 1,000 or 2,000 digits of pi. How do we know what those digits are? Well, we find a series that converges to it, and we can just bring in more terms. And those terms are simple. It's a addition and a multiplication. That's all you have to do. 4 times 1/3, 4 times 1/5. And you can take as many terms as you want, right? We can get pi as accurate as you want by including more terms. All right, I promise you 2 more examples. Here's the second one. By the way, that's an important one. Well, let's do the second example and then I'll catch up. The important. Somebody have a theory for how we can go from the ones we know that we declare important to the natural log?
So the natural log is the integral of 1 over x.
Yeah. So for ln 1 plus x, we're going to integrate number 2. And so I get ln 1 plus x, integrate term by term. I get x minus 1/2 x squared plus 1/3 x cubed. So on. It converges at 1 because it's alternating harmonic. It's exactly the alternating harmonic. And if I plug in 1, I get ln 2 is 1 minus 1/2. So a week or so ago, I told you that the alternating harmonic converges to the natural log of 2. And, you know, I teased you with it. I'm not sure what's going on with the phones. I sure hope it's worth it. Come next Wednesday. And today we proved it. Alternating harmonic converges to the natural log of 2. See you Monday. We're on video. I'll show you this in just a minute. As soon as I get it finished. There's very few online homework problems, so again, look for something to be posted. There are the important.